session number 14 started, my name is Don Davies of Magnuson Klemensic Associates in Seattle, Washington, and today is the first of today's triple track session entitled Advances in Structural Engineering Part 1. The final presentation of this session will be given by Jong-Soo Kim, titled Structural Design of Rechensia Tower. Please help me welcome Jong-Soo Kim.
Good morning. Today I will talk to you about the structural design of Rechensia Tower, which we have done recently. Through the presentation of this specific design, I will focus on how to proceed the design with architects and what is important factors to optimization of structure. I will show you detailed figures, so someone may be bored, but the others are interested with detailed figures. Which one? The Rechensia Tower located. First, let me introduce the building and their design load and the concrete design strengths as presented in Chapter 1. Chapter 2 deals with the gravity load resistance system, the lateral load resistance system, and the structural analysis. As for the last chapter, I will explain the considerations that were made for the structural design. The Rechensia Tower located in Bucheon, not Busan. Bucheon, South Korea, where it is. You can see it on the map. So you can see the Korean peninsula here. And this is. And this Seoul. The actual location of Bucheon is 30 kilometers apart from the center of Seoul. So, as you know here, the Seoul is also 10 million population surrounding the Seoul, Incheon, Bucheon, and the surrounding area. The population of that area is about 15 million, but it's less than the population of Mumbai. It consists of two concrete residential towers. When completed, the tower will be 239 meters high with 66 ground floors and 7 basement floors. The building will be used as apartments, service facilities, and parking spaces. They are reinforced concrete structures. The contract is Ctbuh Engineering and Construction Company of Korea. This building is now under construction and will be completed by the end of next year. When the building's dead load were measured according to the purpose of each floor, as you can see in this picture, basement 6th floor to basement 2nd will be used as parking spaces, and basement 1 and 3rd floor as service facilities. From 4th to 6th floor will be apartments. There will be machinery room on 26th floor and on 62nd floor. This floor will also be used as a belt wall. I will go back to this topic later. Now, allow me to explain how the lateral load was considered. The load was measured according to Korean building code. The seismic load came under seismic zone 1, applied 0.11 G as zone factor. The response modeling factor is 5. This result pertains to building's frame and ordinary reinforced concrete shear wall. In the design of spectrum, the seismic response coefficient, CS, governs the minimum value. This means that the value of CS is equal to that of R, is 3.5. The wind load was measured according to the following chart, the left below. The wind tunnel test has already been conducted when the wind load from the wind tunnel test was compared with the wind load specified in KBC 2005. They were found to be similar. When the seismic load was compared with the wind load, the seismic load was found to be great by 104% in the x direction and by 121% in y direction. The seismic load governs this building instead of wind, such as structure located on inland of the Korean Peninsula. If this locates in Bucheon, a harbor city in front of the South Sea, the wind load governs because the wind load almost double due to on the routes of typhoon wind. Considering the scale of the building, high-strength concrete was used. The difference in strength between the horizontal and vertical elements should be under 1.4 when considering the constructability. As the 26th floor has high concentration of stratus, 60 megapascal concrete, which can resist high stresses, was used for all the horizontal and the vertical elements of the outrigger and the belt wall. Next, I will talk about the building's structure system. As the Rechensia Tower is intended to be luxury apartment, the flat plate system was applied in each typical floor to secure enough floor height. Flat plate improve a building's constructability and speed up its construction. Rechensia Tower's flat plate is 250 millimeter thickness, and its unbalanced moment was examined based on the assumption that the flat plate is an effective girder. The early appearance of base rock in the basement necessitates the use of a slab system that can reduce the floor height to save on the cost of blasting the base rock. The following is a lateral load resisting system. If the core wall is 900 millimeter thickness, the fin wall should be 600 millimeter thick. The flat plate should be considered as an effective girder, and the resistance system should be able to resist the lateral load. As I've already mentioned, both 26th floor and the 62nd floor have a 500 millimeter thickness belt wall, especially the belt wall on 62nd floor needs 60 megapascal concrete to resist high concentration of stresses. The slab of up and low parts of the belt wall were made 400 millimeter thick so that the stress could be transferred. Now, I will talk about how the lateral resistance system was chosen. At the beginning of stage of structural design, a structural engineer positively utilized architectural elements as structural elements. As you see on this picture, the typical floor of this apartment has 5 units. Each unit has a unit wall between, so a structural engineer could make this wall stiffen the lateral system of structure. You can see the effect of these fin walls, how much stiff on the page 11. In the early structure design of the building, the installation of outrigger was considered stiff, sufficient to secure the lateral resistance. Structural analysis was performed with different vertical position of the outrigger for every 5 floors above 10th floor. This graph shows the structural stiffness efficiency for the vertical position of the outrigger. When one outrigger is installed, the optimum position will be about 30th floor. But if two outriggers are installed, the optimized position will be about 20th and 40th floor. The selection process was planned to find the lateral load resistance system that will fit a 66-floor scale. The process consists of 5 steps as follows. Step 1, core wall only. Step 2, core wall plus finwall. Step 3, core wall plus outrigger and belt wall, one place. Step 4, core wall plus outrigger and belt wall at 2 places. Step 5, core wall plus outrigger and belt wall plus effective girder of flat slab. The higher step was processed. The short period consists of from 10.9 to 6.8 seconds. And the same was true for the deformation. That's because the structure acquired more stiffness. Therefore, step 5 was selected. This graph compares the deformation between steps. The displacement for the wind load on the top floor ranges from H2 195 to H2 600. And the maximum drift ratio range from 0.79 to 0.008. You can see the drift ratio is controlled by the belt walls. Let us now compare the stiffness ratio of structures in each step. Suppose that stiffness ratio is 100%, that only a core wall exists. The stiffness ratio will be over 300% in step 5. Comparing the stiffness of each element, the core and the field walls share 70% of stiffness, and the outrigger on 26th floor shares from 16 to 21%. The outrigger on 62nd floor shares 5 to 7%. And the flat plate, the effective girder, shares about 6%. In a 66-story, the outrigger and belt wall, fin wall, have to perform the complex role of structural elements. These are the eigenvalue analysis results. In the first mode, the period is about 7 seconds in the x direction. The second mode shows the y direction. And the third mode shape is rotation z direction. This means that the structure is safe from torsion. The displacement of top floor of the wind load is H2 530 in the x direction and the H2 650 in the y direction. These values are under H2 500, the recommended maximum displacement. The storage ratio of the seismic load is under the 0.01 standard value in each direction. Chapter 3 deals with the special topic of structural design. First, let me introduce the link beam that has been constructed in the core wall and between the wall's openings. The core wall is a box shape, considered the stiffness and the constructability. The link beam is the lintel beam of the core wall's up opening. As such, the high stresses are concentrated in the link beam. To activate the coupling action of the core wall, the link beam has to have high ductility. Therefore, the link beam is constructed using steel beam and reinforced concrete. As for link beam details, a starboard is used to ensure safety in earthquake. The raw floors used as service facilities it would be highly irrational to place the finwall at the plane. As such, a transfer column was designed below the finwall as it was difficult to transfer the load continuously to the transfer column. A special seismic load combination was applied to the transfer column. And H-shaped steel beam was inserted in the transfer column so that the latter could resist the large tension force from a special seismic load. On the basement floor, some fin walls were redesigned to make an anchorage for the transfer column, which has large pull-out resistance on the basement floor. The transfer column, which has a composite section, can achieve anchorage performance through the fin wall of the up and lower floors with stud boards. You can see the location of studs in the picture. As I mentioned earlier, there are belt walls on 26th floor and 62nd floor, which are to be used as machinery facilities. The belt wall is 500 millimeter thick, but some of its corners, which are arranged by stress, are 750 millimeter thickness. The upper and lower slab of the belt wall should bear a large induced plane stress. The stress was evaluated when the analysis reflected 400 millimeter thick plate elements. As a result, the slabs were divided into sections. The shear friction in the connection between the belt wall and the upper and lower slab was examined. Then the connection was designed to transfer the shear force of the belt wall to slabs. In the analysis, the boundary condition of lowest floor, base 7th floor, was set to 6 degrees of freedom, which provided a fixed support. Considering the confinement effect of the grounds and the basement's external walls, I assume that the support was in X, Y, and rotation Z directions on the basement floors and the first floor. Therefore, a large reaction in the lateral direction was induced on basement 1 and the first floor. A diaphragm force was induced to safely transfer the load to the ground of the first floor slab. Due to this force and the construction load, the first floor was designed to be 400 millimeter thickness. The load transfer was examined via detailed analysis of first floor on picture of the right above. As you can see in this picture, a shear friction reinforcement was installed around the core wall and each opening so that the load could be easily transferred according to the result. This is the last. The buildings are two identical towers that provide a podium as they are connected from basement floors to fourth floor. As you can see in this picture, however, the separate movement of the two towers may cause high tension and compression from seismic force on the ground floor. As such, an expansion joint was designed to reduce the strain energy. The expansion joint is located in the side frame with the smallest width. It was with 50 millimeter gap. In some cases, we put it together as a whole floor. The architect or the clients want this one. So we can examine that the analysis. So according to that one, we put more reinforcement if possible. So we can design that way also. This is my presentation on structural design of Rechensia Tower. Thank you.